Hello, everybody. We're now continuing the problem of the pipe network. We have done the part of the or first pipeline and the pump, and now we're gonna go to the next part, which is the splitter and the rest of the pipelines. Um, we have some information about the or the splitter. The splitter called S1, which is this one, the S1 splitter. The it has one inlet stream 3 and 4 5 coming out of it, and there is the flow fraction is 0.805, so it's 80.5% of the flow going into stream number 4. So this is going to be the first thing we are going to do now. So let's look at the splitters. It's going to be in the mixers splitters tab. It is in the F split, which is the flow splitter. There are many shapes, as you see. It's going to be just a block, anything. We're going to use the T that it was used in the textbook. Again, this is one thing which is not gonna make any difference with the calculations or the simulation, but it's important for making the shape of the flow sheet nice. Of course, you see that the T looks like this. The flow goes from this side and comes out of the two other sides. And this is what we're gonna try to do, just to call it S1 as it is. And the first thing, we need to flip it or rotate it 90 degrees. And to do this, is just right click, and from rotate icon, you can find this rotate left. So it's taking this shape. You can find this in the format tab as well. I think it was in the format or modify, maybe in the home. I'm not sure where was it, but it was somewhere here. Oh, we have to select it first, and it should be, yeah, it's here in the rotate part of this ribbon. And now the next step is to connect this stream 3 and then get streams 4 and 5 out of these sides. But if you go to the mode of connecting mode, you'll find that it can be fed on the side, which is not what we expect. And if you try to keep it or make it go in from this side, it's not going to work. So the only way to connect it is to connect it from here, and you would be surprised because it was done here the way that it should be. And the way to do this is to do it manually, to double click on the red arrow and pull it to where you want the feed to be added. It's kind of tedious, little bit. It's not easy. It needs to some training, but this is how it works. I'm not sure why they want to connect it from the side, but anyways, this is how it works. Now we need to get stream 4 and 5 out of the splitter, so we will create a stream 4 and stream 5. Again, the outlet stream will come out of the same place, so we will do the same thing, is to get it out from here and then to change its position. So what I'm gonna do is to pull it the other side so it comes from here. I don't know why. This is how it works. So this is stream 4 and stream 5, and now we need to connect T2 and T3, and we're not sure if these are pipes or pipelines, so you need to go and find more information about T2 and T3. T2 connects of more than one segment, as we see here from the coordinates. It's 0, 0, 2.71, so this is one segment, this is another segment. So T2 is a pipeline, T3 is a pipe. It's just one diameter. So we will do both, and it's nice thing to do that because we will explore the different ways of connecting the or defining the pipes and pipelines. So this is what we're gonna do. So T2 is a pipeline, and T3 is a pipe. So we'll go to pressure changers, go to pipe. And again, just to remember, it is single segment for the pipe, which is gonna go here, and the pipeline will go here. Connect them with the inlet and outlet streams, and connect this here. Rename it. This is gonna be stream 6. This is gonna be stream 7, if I remember right. Yep, and this is T2, and this is T3. Now we need to define these two guys, the pipe and the pipeline. So the first thing I'm gonna define is the pipeline. So to make it easier for me, I'm gonna put them side by side so I can see what I'm doing. We're now working on T2, so this is the inlet stream 4, outlet 6, and we will do the same thing that we did last time. So we are assuming it's constant temperature, and we're not specifying the inlet conditions because they have already been specified before. And the part here is to define the nodes. I'm gonna go back. We will calculate it based on the node coordinates or the segment length. We are using the node coordinates because this is how it's defined here. In the connectivity, we will go here, the inlet node. It's gonna be 0 or node number 1, or it's better to do it inside. It's node number 1. The x coordinate is 0, the y coordinate is 0, the z coordinate is 2.71, and this is 2, 0, and 2.71. So it's 2 meters. The length is 2 meters. So from node 1 to node 2, the I'm gonna keep the roughness. I'm not sure about the roughness. I think we mentioned something about the roughness before. I'm just gonna check it quickly. I don't see anything about the roughness here. Anyways, I'm gonna keep it as it is. I have no information about the roughness, so okay. So we'll use the roughness that's already here. The diameter is 2.5 inch. There is no annulus, so this is done. We need to define the new node, which is node number 2. It's from inlet node 2 to 3, the segment number 2, I'm sorry. And this is gonna be 2.75 and 2.71, and the diameter is 2.5 inches, and that's all. So now we're almost done. We are just missing something in the splitter. We haven't defined the split fraction. So we said it's gonna be 0.805 for stream number 4. This is enough for defining the splitter. And now we'll go to T3. And the nice thing about T3 is, again, we said it's gonna be a pipe, not a pipeline. We can, of course, use a pipeline and keep it just one segment, but I'm interested in exploring both. So here we see that the pipe length is 26.3 meters, and the inner diameter is 2 inches. Whoops, 2 inches, and the elevation, which is the pipe rise, is 0. You can define it by elevation or by angle. So we don't have any elevation here, and we can define it if there are any kind of elevation. So here we cannot use the nodes when we define the pipe. We can use only the nodes if we are using pipeline, but for the pipes we can only use the pipe rise and the pipe length, which I think we mentioned before in the pipeline. Anyway, so now we're done with everything. We can run the file and run in the simulator and see what we get. There is a problem here that we can see. There is something about T2 and T3. Okay. Oh, yeah. Again, this is the same thing that we mentioned before. We have to make sure. Oops. That the flash options is liquid only, and here the flash options is liquid only because This is important for liquid phase. Now the results are available without any issues, and we can now take a look at the output. So for the splitter, let's take a look at the results. There are not going to be a lot of results actually, just the splitting fraction and the balance, how much flow is in and out, and you can see the stream results is going to be the same temperature, same pressure, everything is the same for the inlet and outlet streams, just the flow rates is of course it's going to be different because of the splitting, but the mole fractions is going to be again it's water, so even if we have different components, we will find the ratios are the same. Now let's take a look at the results of the pipeline here. This consists of two segments. We can see that the inlet pressure is in millimeters water 60 435. The outlet pressure is 60 283. There is not a lot of pressure loss. We have all the information here, and if we are interested in the profiles, we can take a look at, for instance, the velocity profile. It's important to know the velocity profile. You can, oh, not the temperature. You can take a look at the profiles from this side here. For instance, you want to see how the pressure changes along the pipeline. You'd see that it changes linearly until it reaches node number 2, and then changes in a different way because I don't know why, but I think the length of the node is the same, and this is kind of misleading a little bit because you think that this length is equal to this length, and actually this is not the same length. We have two parts or two segments with different length and different elevations, so it just puts it as nodes, not as the distances or elevations. So you have to keep in mind that this is not the same length as this. There might be different diameters, whatever the thing that happens, but this is how the results are plotted. In the profiles, you can see also the pressure drop. You can see the velocity profiles. Many things that you can see. Again, it's uniform velocity, so you'll not see any change. And it assumes there is a gas, but there is no gas, so it's have the gas as 0. So anyways, it's not important in this case. The last thing we will take a look at is the pipe, and in the pipe you'd see it's giving less information. You have here the equivalent length, the pressure drop, which in this case is gonna be little high. Yeah, and here this is one thing that's nice to notice. Here you'd see there are three pressure drops: the total pressure drop, the frictional pressure drop, and the elevation pressure drop. And actually this is the sum of these two. So you have the pressure drop coming from two sources, either because of the difference in elevation or because of the frictions that happens in the pipe. And in this case, we don't have any elevation pressure drop, and that's why you'd see that this is the only source of pressure drop is the frictional pressure drop. And here you can see, if you take a look at the pressure, you'd see that this is again it's linear. But let's for instance change something in the pipe rise. I'll make it like 4 meters, and in this case you'd find different results. And in this results you'd see that we have two types of losses, from the friction and from the elevation, and the elevation is way more than the friction pressure drop, and this is what you see, 39,000, and this only 3,000. And if you take a look at the pressure profile, you'd see that again it's linear, but the scale is wider than it was before. So it's nice to find that, and you can double check that. For instance, if you want to recheck the calculations, you can do Bernoulli equations manually. It's gonna be very close to the results that you see here. Using the friction factor, you can go to Moody diagram and get the friction factor and calculate the losses and compare it to what you see here. And it should be a good exercise to do the calculations yourself. I'm gonna put it back to 0 so we can complete the simulation the way it should. And this is all what we get from this stream results. Is gonna be the same. It's not gonna add something more. Just one thing. This is how we can get the numbers that are used to plot the profiles, and that's all. So in the next video, or in the next video, we will see, the rest of the flow sheet. We have two more splitters and the four. In this case, they are pipes. And I think I'm gonna do this, all the connections and everything, before I run the next video, so that we can save some time, instead of doing some tedious work without adding any new value to the viewers. So this is gonna be the topic of the next video, inshallah. So I'll see you then.